drawing good. All right, so December 15th. All right, and I think this is like section 4-6 in our book. All right, we're going to do trapezoid rule. Let's call it trapezoidal rule. And we're going to take a look at Simpson's rule. All right, Simpson's rule, I'm just throwing in there just so that it's simple, it's easy, it's not going to take very long to do it, comprehend it, understand it. All right, Simpson's rule is not going to show up on the ACP test or the AP test. All right, but it's a way of calculating it. We can do some nice comparison with the trapezoidal rule and Riemann sums, and so I want you to see the difference because it's kind of good. All right, now, first of all, we're going to take a look at this trapezoidal rule. All right, and we're going to go conceptual. All right. First of all, you have to know what a trapezoid is, okay? And you have to remember how to calculate the area of a trapezoid. All right, this would have been like 7th and 8th grade math. All right, traditional trapezoid is what? 2 parallel sides. All right, so generally when you were in middle school, you drew trapezoids that look like that. Okay, so here's 2 parallel sides, and then the other sides were whatever they wanted to be. All right, but basically what? You had a couple bases. You had a B1 and a B2. Those were your parallel sides, and then you had a height in there, okay? And that's just the way we drew it when you were dealing with it in middle school, okay? I could also do it like this. There's nothing that said these 2 sides had to be at an angle. Again, my 2 parallel sides, there's my first base, there's my second base, and here's the height, okay? So that's basic trapezoid. All right, now, assuming that you do not have the area of a trapezoid memorized, you may or may not. All right, couple different ways to write the formula. I like to write it just because of the way we're going to do this in calculus. I like to do 1/2 times the sum of the bases times the height. Okay, that's the area of a trapezoid. One way to write the formula, I can sum the bases, multiply it by the height, and divide by 2. Same thing. All right, but because we're going to do this kind of horizontally, I like it in that form. Now, stop and think about what we did with the Riemann sums. What did we do? We used rectangles to approximate the area under the curve. All right, well, nobody said we have to always use rectangles. We can use trapezoids as well. Okay, so let's just kind of generically look at what's going to be happening with this. Okay, so I'm just going to draw a random f of x curve here. Okay, I would have, what I'm going to do is I'm going to take this triangle and I'm going to turn it on its side and I'm going to build it upward. Okay, so if I wanted to estimate this, say from here to some random point over here, I could draw some rectangles, right? Or rectangles. I'm going to say rectangles throughout this whole lesson because I'm going to screw it up. I could draw some trapezoids. All right, here could be base 1. Here might be base 2 of my first trapezoid. All right, that could be my first trapezoid. All right. And then I could draw a second trapezoid. Maybe not the same width, right? Because they don't have to be the same width. All right, there's trapezoid number 2. All right, could I draw a third trapezoid in there? Let's go to a green. Again, let's not make it the same width. Okay, there's trapezoid 3. All right, so if I, just like we did our Riemann sum, just like we did our rectangles, couldn't I find the area of the first trapezoid, add it to the area of the second trapezoid, add it to the area of the third trapezoid, and then I would be approximating the area. Okay, now stop and think about this. All right, that's a trapezoidal rule, okay, in essence. Now let's see, let's do this in origin, see if it, let's do a highlighter color. All right, if I was doing this, let's say with a right Riemann sum, let's overlay a right Riemann sum on this, okay? So if I did that, there would be the first rectangle. If I did a second one, there would be my second one. All right, here would be my third one. All right, now look at those. Look at the Riemann sum compared to the trapezoidal rule. Isn't the trapezoidal rule going to give you a better approximation? Okay, the trapezoidal rule is going to give you a better approximation. All right, when we looked at those Riemann sums, we did the right, we did the left, we did midpoint, and they all gave us different approximations. But when you do the rectangle, you got a lot of excess space up there. Okay, but as soon as I do a trapezoid, look, that chops off that corner basically every time, which makes it a better approximation. Okay. Now, another thing that I want to look at for later, we're going to do another example, and then we're going to do a formula that's always given in the books. And I really hate the formula because I like for you to conceptually understand what's going on here, that we're taking the area of these trapezoids and adding them up as opposed to just memorizing some generic formula. Doing it conceptually the way I have here, probably should have done that. It also helps with the concept of the fact that no one said these trapezoids have to be the same width. All right, now let's take a look at this first trapezoid. All right, it's this trapezoid turns on its side, right? So the bases, this is B1, this is B2. That's how high it is, right? So we're going to plug these values into the function and see what that distance is. And then this in essence is the width, but it's our h here, but it's our width, it's our delta x of the trapezoid. Okay, this was supposed to be a 2, can't hardly see that 2. All right, now let's go to look at the second one. All right, this was the second trapezoid, right? Well, so here's my height, or my delta x, how wide it is. But this height from here to here is B1, and then this is B2. All right, so this number, this height, gets used 2 times, all right? Which I'm going to ask you to remember that, because later when I give you the formula, it's going to make sense. This height is used once because it's on the front rectangle. I told you I was going to say rectangles all day. The front trapezoid, okay? But this distance, it's base 2 of the first trapezoid, but it's base 1 of the second trapezoid, all right? And then same thing, my green go, all right? This third trapezoid again, this is the height, or the delta x, how wide it is, the height according to our old-fashioned formula, but how wide it is, this is how high up the trapezoid goes. All right, but this is B1. So this distance is used as B2 in this trapezoid, but it's B1 in this trapezoid. And then this would be B2. Okay, so what can we conclude from this? This first height is used 1 time. All of the inside heights are going to be used 2 times because this height is used for the first trapezoid and the second one. This height is used for the second one and the third one. And then when we get to the end, when we finally get to the last trapezoid, this one again is only used 1 time. So these are used 1 time. Any height in the middle is used 2 times throughout the whole thing. Okay, so again, put that back in the back of your memory, because when I show you the shortcut formula thingy that's in the book that only works for equally width trapezoids, you're going to see a pattern right there. Okay. All right. So hopefully that's enough background information, all right, that we conceptually understand that. How we doing? Anybody got questions yet? Okay. I'm going to take your silence as a we're good. All right. Now I did pre-draw this, so I'm going to talk a little bit here and while you write it down. Okay. So we're going to actually do this example, and we're going to do it in 2 different ways. Obviously, I have something hidden underneath here because that's a little piece of paper. All right, but we're going to look at it from a pictorial standpoint, because I want you to be able to see it from a graph. We do everything, multiple ways. So from a graph, from an algebraic standpoint, from a table of values. Okay, so we're going to start with our graph here. It's just a random function. And again, looking at this, I did not give you the actual function, and that's okay. The AP test really likes to do conceptual questions without giving you the actual function. When you do your homework out of the book, you're going to be given the function a lot. Okay. And all I did here was just kind of re-emphasize, okay, this is our trapezoids going up. We've got a base 1, a base 2, and then I called this our height, okay, or our width. All right, this is the formula, 1/2 times the sum of the bases times the width. Okay, this is the height going up. This is the width. Okay. All right, so hopefully I have yacked long enough that you're coming close to getting this drawn. All right, I tried to be very specific in where I put those points. The only thing I labeled was what was over here on both of those. All right, now let's say this says use the trapezoidal rule to estimate the area of f of x on the interval from 0 to 12. Okay, on the interval from 0 to 12, we want to estimate the area. All right, now we're estimating the area using a trapezoidal rule. We're still going to do the Riemann sum here. See, we're going to go, all right, we're going to do an integral. Did I say Riemann sum again? I'm really stuck on that. We're going to start with our integral from 0 to 12, all right, of, all we know is f of x because I don't really know the function, dx. All right, now, since I am estimating it, all right, I can't actually calculate the actual area because I don't know what the function is. All right, but I can approximate this area using our trapezoidal rule. All right, now, what would I have up here? I'm going to have the way I have divided this up and given you the points that I have done. What I'm going to have, I'm going to mark this all up again. I'm going to have a trapezoid right here. Okay, that's my first trapezoid. I'm going to color code this. All right, so this is my first trapezoid. All right, so every one of these, 1/2. All right, now I need the sum of the heights. All right, so this one goes up to 8. This one goes up to 10. So 8 plus 10. And then how wide? What's the width of it? It's a width of 5. So that's my first trapezoid. Okay, then I'm going to add to that the next trapezoid. Okay, so let's put it in blue. So the next trapezoid is going to be here. So there's my second trapezoid. All right, so it's always 1/2. All right, sum the heights. All right, so this height is a height of 10. See, and there's that number getting used twice. All right, and then the height here, which is 12. And a width of 1. You see how doing it with the formula, it's okay that they're not the same width. All right, anytime you are trying to do this and it is not equal subintervals, equal widths, you have to do it in this way. Okay, I cannot emphasize that enough. All right, let's go ahead and make the last one in green. So then my last one would be, ooh, that's not a very good drawing there, but close enough. All right, there's my third trapezoid right there. All right, so we started out with a 1/2 always because that's in our formula. All right, and then we do, okay, how high is this one? It's a 12. Again, notice how that number is getting used twice. Okay, and then this one has a height of 15. And it has a width of 6. Okay, so this was my third trapezoid. This one is my second trapezoid. And this one is my first trapezoid. All right, so this is nothing other than our Riemann sums, except instead of using rectangles, we're doing it with trapezoids. All right, so then it's just a bunch of math. Can you do it and not screw this up here? Okay, so let's see, that's going to be, I'm going to divide by 2, like 45. I'm just going to do the math really fast here. This is arithmetic. You don't need help with the math. It's going to be like 11. This is going to be, if my notes serve me right, 81. Okay, so I'm going to have approximate area of 137. All right, so we all good? Dead silence again. I'm assuming we're all good. Okay, all right. Now, we look at these, we look at everything from more than one perspective. So this is from a graphical perspective. I don't know the function, but I have the graph, so I can pull the numbers off of the graph. Okay, now, let's suppose they did not give you the graph, but instead they gave you the exact same problem, but they gave it to you in a table of values. All right, if I have a table of values, it's the exact same thing as the picture. Okay, if I plug in 0, I get out an 8. If I plug in 5, I get out a 10. If I plug in 6, I get out 12. If I plug in 12 for x, plug it in the function, I get out a 15. Okay, so this is the exact same as this. It's just in a different format. It's in a table of values. Okay, now, if you don't have the picture, you're not going to draw a picture. You're just going to look at the table, just like we did a Riemann sum from a table. Okay, now what I am going to look at, where are the bases? All right, so this 8 and 10, and then 10 and 12, and 12 and 15, where are these? It's these numbers right here. So this right here is my bases. These numbers right here, because that's how high, when I put n of 5 into the function, how high does it come out? Well, it goes to 10. All right, and then my width of each trapezoid, the 5 and the 1 and the 6, comes from here. Okay, comes 5 minus 0 is 5, 6 minus 5 is 1, 12 minus 6 is 6. All right, so let's kind of put this on here. So my first trapezoid, in essence, involves these numbers right here. Now I am going to show an overlap. There really shouldn't be an overlap, but all right, here is these numbers I'm going to look at for trapezoid 2. All right, 6 minus 1, my bases are down here. Okay, trapezoid 3 is right here. Okay, so the heights 12 and 15, subtract up here, 12 minus 6 gives me a width of 6. Okay, so without doing one back in there, without doing a whole entire another problem, all right, this is what it looks like from a table standpoint versus a graph. Okay, y'all good? I'm going to switch out and go to gallery. Are y'all still with me? Y'all still with me? Bright, smiley, shyly faces. Okay. All right. Okay. You're awful quiet this morning, so that's why I'm checking. All right. Now, what I am going to do, even though I don't like it, for the most part, if you do this on every test, if you actually do the 1/2 plus the sum of the bases times the height on every one of them, I mean, that's perfectly fine. All right. If you never want to use the shortcut, I am going to show you the shortcut. It's in our formula, or it's in our book. And it has a nice little formula for it with a definition. So let's go ahead and do that, mainly just because it's in the book. And it is, if you have equal subintervals or equal width trapezoids, it is faster, I think. Okay, so let's say we have trapezoidal rule. Okay, all right, we're going to let f be continuous on the closed interval from A to B. Okay, the trapezoidal rule. For approximating the integral from A to B of f of x dx is given by the integral from A to B of f of x dx is equal to b minus a over 2n times, now I'm going to color code this, and hopefully this is going to stand out on why I'm color coding this, a 1 times f of x sub 0 plus 2 times f x sub 1 plus 2 f of x sub 2. All right, let's go plus. Now I'm not going to keep going here because we could go forever and ever and ever and ever and ever until we get to the end. And then it's going to be 2 times f x sub n minus 1 plus 1 f x sub n. All right, I will explain here in a minute. Okay, so this type of thing, x sub 0, x sub 1, x sub 2, et cetera, forever and ever and ever until we get to an end, and then eventually we're going to stop, right? So this would be x sub n, this would be x sub 1 minus n, whatever would be right before it. Okay, so it increasing and decreasing all the way through here. All right, now notice I color-coded the coefficients, 1, 2, 2, 2, 2, 2, 2, 2, and 1. All right, well, why did I do that? All right, why did I do that? Let's go back to this picture here. This first rectangle, again, I said rectangle, I told you I was going to do that all day today. The first trapezoid, this height is used one time. This one is used 2 times. This one is used 2 times. Everything in the middle is used 2 times. This height on the end, on the right-hand side, is used once. This height is used 1 time. All right, that's where those coefficients come from. 1, these 2 on the ends are the heights of the 2 trapezoids on the outside edge, and they're only used once. Every other height that you generate in the center is used 2 times. All right, now this is under the assumption that every one of your trapezoids has the exact same delta x. It has the same width. Okay, so you're not, I'm almost positive, going to be able to guarantee, say you are not going to be able to use this on the AP test, because they hardly ever make them have the same width. All right, this is going to help you with the book questions out of your textbook because they do standard widths. Okay. All right, now let's do one question that'll help you with just your basic homework, standard width questions, and we'll use this formula. Okay. All right, so oh, go ahead.
Can we still do the other way, even if they have a standard width? It's just more work.
Yes, yeah, you'll just have to write out more stuff. But yes, you can do the other way. And in some years, sometimes I don't even show this sometimes. All right, because like I will guarantee you somebody in the room is going to try to use this on a table of values, like for this question right here. All right, someone is going to try to use the 1, 2, 2, 2, 2, 2, 1, and it doesn't work because they're not equal widths. All right, and so that's why sometimes I kind of avoid this whole entire thing. But then other times it's like, no, you ought to conceptually be able to, if it's equal widths, I can do the shortcut. If it is not equal widths, then I have to do it the long way. Okay, so I go back and forth every year on this, so whether I'm going to do it this way or not. Okay, so let's suppose it just tells you to approximate the definite integral, and I'm going to abbreviate so that we can not write so much stuff here, using trapezoidal rule. Again, I'm going to abbreviate. Okay, so we're going to approximate the definite integral using the trapezoidal rule. Okay, so what they're going to do in your textbook is they're going to give you the function. All right, they just want you practicing this concept. So let's say they give you the integral from 0 to 2 of 1 over the square root of 1 plus x to the third dx. All right, and obviously not a nice function. So this is, you're going to definitely use calculator on this. I'm not worried about the arithmetic part. It's the setup part. Then they're going to tell you n equals 4. So that means 4 subintervals and of equal width. Okay, so now again, we're running from 0 to 2 and we need 4 equal intervals. All right, so what do I like to do? All right, we don't need to draw the whole darn picture, but it's nice if we have the little section number line to look at. So here's 0. All right, we're going up to 2. All right, now I could do the math to find the delta x if I want, or you guys can just divide it up into 4 equal ones, but let's assume we're showing the math here. All right, so I can calculate delta x by what? That's the b minus a over n formula. All right, if you actually want to do it that way, you can. All right, so what do we got here? We got 2 minus 0 all over 4, because 4 is in. So 2 over 4 is a half. All right, most of you, though, could have come up and figured out that, oh, if I'm going from 0 to 2 and I'm 4 equal intervals, they have to be a half a piece anyway. All right, so here's 1/2. Here's 1. And there is 3/2. Okay, now let's go back and look at the formula. All right, if I'm doing a trapezoidal formula in the book, I also need to calculate b minus a over 2n. All right, because this is equal intervals, and so they've factored this out. Okay, so let's make that calculation here. So b minus a over 2n. All right, it's going to be really, really close. We'll have a 2 minus 0, and then a 2 times a 4, which is what, 2 over 8, which is a 1/4. Okay, so that calculation is strictly for our trapezoidal rule. Okay, now let's go ahead and answer here. Oh, lights are going off again. Okay, so integral from 0 to 2, 1 over square root of 1 plus x to the third dx. All right, I'm approximating. All right, according to that formula for trapezoidal rule, I got to have my b minus a over 2n, which is a 1/4. Okay, then I'm going to use my 1, 2, 2, 2, 1 thing. All right, and I will put in every point, because why? I've got a trapezoid going up here, I got a trapezoid going up here, I got a trapezoid going up here, I got a trapezoid going up here. Okay, so this will be 1 f of 0 plus, now I start my 2's, 2 f of 1/2. All right, and by doing this f, I am assuming that my function is f of x. All right, I am going to assume the function is f of x. Okay, plus 2 f of 1 plus 2 f of 3/2 plus, okay, now I'm down to my last one. So it's a 1 f of 2. So there you see the 1, 2, 2, 2, 1 concept. Okay. All right. Now this seriously is all arithmetic. All right. I don't know that we need to waste our time doing the math. You can do this. You plug this into the function. You'd use calculator, times it times 1. Plug this in the function, multiply it by 2. All right. So we're going to save some work here. I'll go all the way down to 1/4 times. This turns out to be like 5.589, something. All right, because that's square root in there. If you really want to do the arithmetic, you could do the arithmetic, but I went out 3 places there, so that's roughly that. All right, so you will have questions in your textbook. It's going to be set up just like this. They're going to give you a nice little integral. They want you to approximate. They'll tell you how many equal intervals you've got. All right, if you want to use a shortcut, that's fine. Okay. All right, so I think that's pretty much trapezoidal rule. Okay. We have questions on trapezoidal rule. Okay, now I want to do Simpson's rule here. All right, but I want to do, the reason Simpson's rule is, I mean, it's in your textbook, it's kind of cool to look at, but it's not used because it would just be cranking out a formula here. Let's take a look at a visual comparison before we go any farther. Okay. All right, this is a visual comparison of all our different approximation methods. Okay, so we did a Riemann sum and it uses rectangles. All right, so I just chose, let's see, what are those right-handed endpoints? Okay, and you can see that this is kind of not a good approximation. All right, then you've got your trapezoidal rule, which we just learned. It uses trapezoids. All right, so you come up and then draw a trapezoid there, and with this side being that angle, makes it a better approximation. Okay, so then we've got Simpson's rule. Okay, so probably just another guy that wanted to, come up with something that's really famous here. So it's complicated, but yet it's not complicated. He come up with, okay, well, let's come up with a P of X curve that kind of goes through all of these points that we want, and it'll be an even better approximation. Okay, so it uses curves up here. Well, because it uses curves, I don't have a formula for that right here. This was length times width. This is 1/2 times the sum of the bases times the height. But if I draw something and have a curve up here, then I really can't do what we've been doing, as in the area of this plus the area of this plus the area of this plus the area of this. So you actually have to have a formula very similar to our 1, 2, 2, 2 formula. Okay, but each one of these just gets to be a better approximation, And I think on your homework, I don't remember exactly. I think maybe it says to do a Riemann sum, then a trapezoidal rule, or it says do trapezoidal rule and Simpson's rule. And what you're going to see is the numbers are going to, your answers are going to be really, really, really close because they're all approximations, but then they will just keep getting better. If you use these two, this should be a better approximation. If you use these two, this should be a better approximation. Okay, so a visual representation, you can get this. This is in my online notes. So if you want this, a copy of it, you can download this. Okay, all right. Now, with that being said, let's go ahead and look at a formal definition of Simpson's rule and then the nice little formula here. Okay, so Simpson's rule. All right, so we're going to let f be continuous on the closed interval from A to B, and we're going to let n be an even, that's important, integer. Okay, so what n N is the number of subintervals. Okay, so Simpson's rule is only going to be used when we've got an even number of subintervals. Okay, Simpson's rule for approximating the integral from a to b of f of x dx is, okay, we've got the integral from a to b f of x dx. And this is going to be approximately equal to, now out in front, this is going to be a b minus a over a 3n. All right, now again, I'm going to color code this for you. I want you to watch at the coefficients here. I'm going to have 1 f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3. Okay, and then we're going to keep going here. All right, now last two terms, all right, is going to be then a 4 f of x sub n minus 1 plus 1 f of x sub n. Okay, so if nothing else, it's a nice, cool little pattern. All right, again, see what we're doing here. Okay, we're doing a 1. All right, always starts at a 1. All right, and then it goes 4, 2, 4, 2, 4, 2. They alternate. When you get to the very end, it'll always end with a 4 and then a 1. Okay, because how are we guaranteed this? Because we're doing even subintervals. Okay, so you just pay attention to your little coefficients there. You plug it in. So to do this, then you really do need to have the actual function. And since your textbook leans towards the fact that they give you the function and then they tell you how many subintervals, then that's kind of why they throw this in here. All right, so we're going to do one example of this because I think it's straightforward. We're going to plug it in, plug things in that we need. We'll calculate this. Okay, just one example. And I think we
Can you leave it up for 1 second? I'm sorry.
sure can. There we go. Just let me know when you're done.
I'm good, thanks.
Okay. All right, so we'll go ahead and do some directions here. Let's say it says to approximate the, again, I'm going to abbreviate the definite integral using Simpson's rule. Okay, so there's our directions. All right, and your textbook's going to do what? They're going to give you the definite integral. Let's do this with a trig function. We haven't done one of those for a while. So let's say we're going from 0 to pi. All right, and then let's say it's sine x dx. All right, trig functions are fine. Let's say we've got n equals 4. All right, I have to have an even number here to use Simpson's rule. Okay, has to be even. Okay, so we're going to do exactly what we did before. Okay, we're not going to draw the whole darn thing out, but it's good to have the little number line. So I'm running from what? 0 to pi. And I got to have 4 sections. All right, now most of you can do that without doing your delta x, but you can calculate that delta x. All right, b minus a all over n. So that would be a pi minus 0 over 4, which is going to be a pi over 4. So we know each one of them is going to be pi over 4. So that means, let's try to get 4 in here equal. Okay, so that means this one's going to be pi over 4. All right, half pi is going to be pi over 2. All right, then that's going to make this one 3 pi over 4 because they're each 1 pi over 4 apart. Okay, all right, so like I said, you don't necessarily have to do this calculation if you can do it without it. All right, now for Simpson's rule, we need to calculate b minus a over 3n. Okay, so if I do that one, I'll have a pi minus 0 over 3 times 4. So that's going to give me a pi over 12. So that's going to be the number that's going to go out in front. Okay. All right. So we always want to start with our integral. So here's our integral from 0 to pi. We're doing this of sine x dx. Okay, so we're going to approximate this. Okay, our formula says to start with this number, which we calculated as pi over 12. All right, and then we alternate and we do our funky things with our coefficients. So 1, and then 4, 2, 4, 2, 4, 2, till we go all the way down to the end, and it's a 1 again. So this will be 1 f of, all right, now again, we're going to use every one of these, okay, every one of these. So this will be f of 0. All right, then I was supposed to go to a 4. So 4 f of pi over 4. All right, then the next one was supposed to be a 2. So 2 f of pi over 2. All right, the next one, we're alternating 4s and 2s. So here's 4 f of 3 pi over 4. That is the next to last one. And I said you would always end with a 4 and then a 1. All right, so now this is our last one. So 1 f of pi. Okay, now on this one, all right, unit circle would come in really, really handy here. All right, there's no reason why we can't do this on a unit circle. I'm going to do a little bit more detailed than I did on the last one. All right, so if I plug in this, what am I going to have? I'm going to have 1 times the sine of 0. All right, plus on this one, I'm going to have what? 4 times the sine of pi over 4. I'm actually doing that because I want you to see it like with our unit circle here. 2, and then times the sine of pi over 2. And then 4 times the sine of 3 pi over 4. And then 1 times the sine of pi. All right, so you're pretty much just using straight unit circle here. Okay, let's see. Sine of 0. Sine of 0 is 0. All right, pi over 4, well, is what, square root of 2 over 2? So I'm going to have a 4 times the square root of 2 over 2. See how we can avoid decimals on this? We use our unit circle. All right, this is going to be 2 times, let's see, pi over 2. Sine of pi over 2 is 1. 4 times sine of 3, 4 pi, pi over 2, or square root of 2 over 2. And then sine of pi is going to be 0. All right, so again, I'm not going to finish this all out massively here. We end up with a pi over 12 and then 2 plus 4 square root of 2. All right, if you want a decimal approximation, I think it comes out to be 2.005. All right, but this, do this off your unit circle if you have like sine or cosine function, something like that. That way you're not going to have decimals unless maybe at the very end, because otherwise you'll have something with a bunch of radicals there. All right. But Simpson's rule really is crank out the formula that they give you in the book. All right, you got to remember how to come up with this number. That's that formula right there. And then you got to remember to alternate your 4s and 2s in the middle with 1s on the ends. Okay, so there's kind of a plug and chug one on that one. All right, so do we have any questions? Did I go too fast?